Hello, welcome to the lecture number 7 of the course Quantum Mechanics and Molecular Spectroscopy. Before we proceed with lecture number 7, in the previous 2 lectures we looked at the perturbation theory of 2 states. So, to begin with, we had H naught acting on 1 will give E1 1 and H naught acting on 2 will give you E2 2. Okay. Then we had perturbation time dependent, which was H prime of t, and this when added to H naught will give you the total Hamiltonian H. And then we went about by solving the Schrodinger equation IH bar d by dt of psi of x comma t is equal to h to psi of x comma t, where psi of x comma t is given as a1 of t e to the power of minus I e1 t by h bar 1 plus a2 of t e to the power of minus I e2 t h bar 2. Okay. So, after doing all the required mathematics, we arrived at a1 dot of t is equal to 1 over I h bar a2 of t e to the power of minus I omega 21 t 1 h prime of t 2 and a2 dot of t is equal to 1 over I h prime a1 of t e to the power of I omega 21 t 2 h prime of t 1. Okay. So, these two are the coupled differential equations between A1 and A2. Okay. Now, I told you, since they are coupled differential equations, solution of A1 will depend on A2 and solution of A2 will depend on A1. Okay. Now, we used a very simple approximation in which we said there is a perturbation, a constant perturbation that is switched on at time t is equal to 0. Okay. So, that perturbation is something like this, t when it is equal to 0, so some constant value v. In such scenario, then we can written as 1 h prime of t 2 is equal to h bar v and 2 h prime of t 1 is equal to h bar v star. Using these conditions and doing little more about math, we came about we converted the equations into second order derivatives and finally came up with a solution, that is a1 of t equals to a e to the power of I omega t minus b e to the power of minus I omega t into e to the power of omega 21 t by 2, where omega is given as half of omega 21 square plus 4 times modulus of v square to the power of half, and a2 of t is equal to a e to the power of I omega t plus b e to the power of minus I omega t e to the power of omega 21t by 2. Now we said A12 and A2t, A1t and A2t are phase shifted with respect to each other by pi by 2, because this is like a sin theta function and this is like a cos theta function. So which means whenever A1t increases, A2t decreases. They are out of phase with respect to each other. We know functions sin theta and cos theta are out of phase with respect to pi, out of phase by pi by 2. So whenever sin theta goes up, cos theta comes down and the other way around. So based on this, we came up with what is known as Rabi oscillations. So Rabi oscillations are between two states E1 and E2, where the population of states 1 and 2 will go up and down out of phase with respect to each other. Okay. And this is the perturbation theory of the two states. Now let us start with the perturbation theory of n states. Okay. Generalized perturbation theory, generalized time dependent perturbation theory is what we are going to start now. Okay. In such scenario, we will again start with an assumption that we know an Hamiltonian H naught for which there are n solutions, okay, such that this give you En psi n, and n will go from, for example, 1, 2, 3, etc. Okay. So where this represents the quantum number. Now we know that if psi n forms a complete set, okay, so any arbitrary function chi in the same variable can be written as sum over I Ci psi I. Okay, this is something we already know. Okay. So a wave function psi can always be written as sum over n, okay, Cn of t psi n e to the power of minus I E n t by h bar. Okay. So a time dependent wave function is a linear combination of all the wave functions psi h and their phase factors and their time dependent coefficients. Now if we have the time dependent perturbation, which I will call it as h prime of t, this is my time dependent perturbation, then my whole Hamiltonian H will be nothing but H naught plus H prime of t. So when I know the total wave function psi and H, I can solve or attempt to solve the time dependent Schrodinger equation, which is nothing but I h bar d by dt of psi is equal to h psi. So we will do the same treatment that we did for the two states, but in a slightly different manner. Okay. Now let us get to it. So my time dependent perturbation theory is I h bar t by dt of psi is equal to h psi. Now what is psi? This is nothing but I h bar d by dt of my psi is a n sigma over a n of t e to the power of minus I e n t by h bar n. Okay, that is the wave function psi n. You can go and look it back. So my n is this, psi is this. So I am just I've just used this form, okay, equals to h is nothing but h naught plus h prime of t, this acting on sigma over a n t e to the power of minus I e n t by h bar n. Okay. Now once again here we have two sides LHS, this is equal to LHS, this is equal to RHS. So what we will do is we will evaluate LHS and RHS separately and then equate them at a later stage. Okay. So let us start LHS. LHS equals to IH bar d by dt of psi. This is nothing but sigma over n of t e to the power of minus I e n t by h bar n. So this is nothing but I h bar. Okay. Now each term will have two things, that is a n of t and e to the power of, so this is function f of t and this is function g of t, and of course the wave function n is itself time independent, so it will not be able to take a time derivative of it, it is just a constant. So each term, so this is summation over n, so you will have as many terms in this as the number of wave functions in your complete set. So if there are 20 wave functions in the complete set, so this expansion will be for 20 terms, and if there are 100 wave functions in a complete set, then this expansion will be of 100 terms. If there are infinite number of wave functions, then this expansion will be of infinite number of terms. Okay. Now in such a scenario, each term of course will be of two functions. So when you take a derivative, you use the product rule, and so what you get is IH bar. Okay. Now I will take the derivative with respect to n, so sum over n a n dot of t e to the power of minus I e n t by h bar n sigma over n I e n by h bar a n of t e to the power of minus I e n t by h bar acting on n, right, something like that. So I am just going to rewrite it in a way, is equal to IH bar sigma over n a n dot t e to the power of minus I e n t by h bar n, and here this I and this I will become minus 1 and there is already minus n, it will become plus. So plus, and this h bar and this h bar will cancel. So what we will get is a n of t e to the power of sigma over n in minus I e n t by h bar e n n. So you will get two terms. Okay. But of course each of these terms is summation of many terms depending on the value of n. So, you remember this, my LHS is this. Okay. Now, let us look at the RHS. What is the RHS? RHS equals to H naught plus H prime of T acting on sigma over n a n of t e to the power of minus I e n t by h bar n. So, this is nothing but when H naught acts, H naught is time independent. This is just not kinetic energy and potential energy operators of the original Hamiltonian, and we know in chemistry we said that the original Hamiltonian, that is independent of time. Okay. So, H naught when acts on this, so this will not act on a n or e to the power of minus I n t, just acts on n and gives you sigma over n a n of t e to the power of minus I e n t by h bar. When H naught acts on n, we will get E n n. That is the first. And the second term will be plus a n of t e to the power of minus I e n t by h bar, and h prime of t will act on n. Okay. So, that is the two values, of course there is sum over n here. Now, let us equate the LHS and RHS. Now, my LHS was, so we have to now make LHS equals to RHS. So, LHS was sigma over n a n dot t I h bar e to the power of minus I e n t by h bar n, that is mass LHS. Okay. Plus sigma over n a n of t e to the power of minus I e n t by h bar e n n, that should be equal to my RHS, which is nothing but sigma over n a n of t e to the power of minus I e n t by h bar e n n plus sigma over n a n of t e to the power of minus I e n t by h bar h prime of t acting on n. Okay. Now, we will see that the second term of the LHS is equal to the first term of the RHS. Okay. So, we can cancel these two. Okay. So, what we end up in this case is I h bar sigma over n a n dot t e to the power of minus I e n t by h bar n equals to sigma over n a n of t e to the power of minus I e n t by h bar h prime of t n. Okay. So, this is what you get. You can go back and quickly look at the two-state perturbation theory. This equation looks very similar when n is equal to just two state. When n is equal to 1 comma 2, then this equation is exactly equal to what we got for the two-state perturbation theory. However, in this case, since we are starting for n states or many states, a generalized form can be written like this. Okay. Now, what I am going to do is that I will start with the equation IH bar sigma over n an dot of t e to the power of minus I e n t by h bar to n is equal to sigma over n a n of t e to the power of minus I e n t by h bar h prime t acting on n. Okay. Now, let us quickly do the multiply with psi m star on the left and integrate. So, if I do that, I will get IH bar sigma over n a n dot t e to the power of minus I e n t by h bar m n. Now, of course, psi m star equals to n. This is equal to n a n of t e to the power of I e n t by h bar m h prime of t n. Okay. So, this is my this one. Now, we know that the wave function psi n, this is nothing but n, they form complete set, and they are the solutions of the Hamiltonian H naught. Therefore, the integral mn is equal to delta mn. That means, when m is equal to n, this integral, the overlap integral will go to 1, otherwise it will go to 0. Okay. Now, if you plug in that, so which means for anything other than value of n is equal to m, so left hand side, if you take left hand side, for anything for n is equal to m, okay, this term will survive. LHS, for n is equal to m, LHS will survive. Else it will go to 0. Okay. So, which means that LHS will now be equal to sigma over n IH bar a n dot t e to the power of minus I e n t by h bar m n. So, only when m is equal to n or n is equal to m, this will survive. That means, you can drop the summation, this will become IH bar, okay, a m dot t e to the power of minus I e m t by h bar, because for n is equal to m, this will go to mn will go to 1, and m is not equal to n, this integral mn will go to 0. That means only one term will survive, all the rest of the terms will go to 0. Okay. Now, if you look at the RHS, this will be equal to sigma over n an of t e to the power of minus I e n t by h bar m h prime t n. Now, if you take the integral m h prime t n, okay, this integral will be 0 if m is equal to n. Okay. Now, you can see that this is going to, because what you are looking at is you are looking at the transitions onto itself. Okay. You are looking at the transitions of itself when m is equal to n. You know that we can't look at transitions of from a given state to itself. Okay. That means only the terms m h prime t n, okay, will survive if m is not equal to n. Okay. Now, which means I can rewrite this equation as I h bar a m dot t e to the power of minus I e m t by h bar should be equal to sum over n not equal to m. So, now you can take all these terms except that when m is not equal to n. So, when m is equal to n, of course, I told you this will not survive, okay, m not equal to n, a n of t e to the power of minus I e n t by h bar. Okay. So, this is the equation that we need to deal with. Okay. We will stop here for this lecture and continue in the next lecture. Thank you.